right, this last section we're going to break into 3 days because they're kind of like 3 different scenarios that we're looking at. And so we're going to be looking at different types of improper integrals. So the first type that we're looking at today is instead of having a definite integral where a and b are finite numbers, so this interval ends, we're going to look at intervals where maybe we're going from a to infinity, or maybe we're going from negative infinity to b. So what do we do about that? Tomorrow we'll talk about what to do if there's some sort of discontinuity between a and c, like maybe f of x is not defined at 0 or something like that. So improper integrals are different than improper fractions. This is an improper fraction. Improper integral just means you have an infinity as one of your end bounds, or there's some discontinuity, like right here, x can't equal 2. All right, so some vocab. An infinite discontinuity, which again, more on this later, would be where f of x may have a vertical asymptote or some sort of undefined place. So the limit as x approaches c, whether it's from the left or the right, could equal positive or negative infinity. What we will be doing today are evaluating integrals and determining whether they converge or diverge. So converges, an interval converges if it really does have a finite sum. So if we can get the integral from a to infinity of whatever, f of x dx, if it comes out to a numerical answer, whether it's 0 or 1 or whatever, 5 halves, something like that, then that integral converges. If we have an integral that diverges, it means we've evaluated the integral from a to infinity, and that integral came out to infinity or negative infinity. It means that this integral never stops adding up. And so the first sort of stipulation is that you've got to have f of x needs to be something decreasing, because if we're talking about the area between the curve and the x-axis, you definitely need the curve decreasing for it to be able to have some sort of finite sum. But then it's all about the rate at which f of x is decreasing. If it decreases too slowly, then it will never stop adding up. The sum will keep increasing. But if it decreases fast enough, then you will ultimately get like you're adding something close to 0 very quickly, and so you'll have a finite sum. All right, we're going to focus on not part 3, but 1 and 2. So if f is continuous on this interval a to infinity, and we can integrate from a to infinity f of x dx, as long as we use limit notation. So notice, and you have to write this for the AP test. I notice that people tend to leave off their limit notation, and it could be the difference between, that would be like the difference between a 4 and a 5 probably. So limit as b approaches infinity, the b is replacing the infinity right here. And so then that gives us some sort of definite integral we can find the antiderivative of, and then we can evaluate and do limits at the end. Similarly, if f is continuous on the interval negative infinity to b, then you can replace the negative infinity with the limit as a approaches infinity. And then you've got, again, the integral from a to b. And we'll talk about scenario 3 tomorrow. All right, so take a look at this integral. We're going from 1 to infinity. 1 over x is defined on that interval. And we want to get rid of this infinity by saying, well, this is just equal to the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Keep your limit notation until you actually take the limit. So we've had that rule before. This can get kind of annoying, but it's okay. We can integrate 1 over x. That becomes natural log of the absolute value of x. And we're evaluating from 1 to b. I still need my limit notation because I need to show that I've used the fundamental theorem of calculus. So I need to show that this is the natural log of b minus the natural log of 1. Remember that the natural log of 1 is just 0. So now we can get rid of our limit notation because we're going to use direct substitution. The natural log of infinity is infinity. So what this tells me is that this integral came out to infinity, which is not a finite sum, right? So that means that this integral diverges. This even though 1 over x is a decreasing function, it does not decrease fast enough. And so the area between the curve and the x-axis will continue to grow as we allow x to approach infinity. E to the negative x, so that's 1 over e to the x. So that is a decreasing function. And again, we're going to get rid of our infinity up there by saying the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. That's an easy little integral, but you do have to do u sub, so don't forget about all your little integral rules. U is negative x, du is going to be negative dx, so we're going to have to put in a negative and balance it out. So when I integrate this, I get negative e to the negative x from b to 0. I strongly advise you to rewrite negative exponents before you plug values in, or at least as you're plugging them in, rewrite. So instead of making this negative e to the negative b, let's make it negative 1 over e to the b. So rewrite your negative exponent as a positive exponent in the denominator, minus negative, so plus 1 over e to the 0. That makes a difference, a big difference with limits, about whether you're concluding that the limit goes to infinity or does it go to 0. So when I get rid of my negative exponents, it's easier for me to see when I plug in infinity, I get negative 1 over infinity, which is 0, plus 1 over 1, which is 1. So that tells me that because I got a number here, this integral is equal to 1. That's the area under the curve from 0 to infinity under the curve e to the negative x. And so therefore, this integral converges, and it converges to 1. All right, last one on this page, 1 over x squared plus 1. Remember, this is going to be arctan. You want to get in the habit of recognizing that. We need to take care of this infinity, so same idea. This equals the limit as x approaches b of the integral from 0 to b of 1 over 1 plus x squared, or x squared plus 1. That's the limit as x approaches b of, so arctangent is 1 over a. Well, a is 1, u is x, du is dx. So 1 over 1, I'm not going to write that. I'm just going to get arctangent of, should be u over a, but x over 1, just be x again. We're going from 0 to b. Keep your limit notation one more time because you've got to plug in x approaching b. So we've got to plug in our fundamental theorem. So arc tan of b minus arc tan of 0. The arctangent graph is a good one to have in your mind. It has horizontal asymptotes at plus or minus pi over 2. And it looks like a tangent branch, but kind of rotated around, I guess. So the limit as x approaches infinity, yeah, b is infinity. So the limit as x approaches infinity is pi over 2. And arctangent of 0 is 0. So I got pi over 2 for this one. That means that this integral converges, and it converges to pi over 2. So converges to whatever the sum is, diverges. We don't say diverges to infinity, but I guess you probably could. All right, so some other examples. The integral from 1 to infinity of 1 minus x times e to the negative x. U sub is not going to work. I would let u equal the exponent, but that's not going to take care of this. We just did these a couple days ago. I have the product of an algebraic expression and an exponential. And so this should be integration by parts using Lyautey. So you can use either the formula or the tabular method, which is still the formula. You're just sort of shorthanding it, I guess. U needs to be the algebraic piece. dv needs to be the exponential. Remember that you're taking derivatives of u until you get 0, because that's algebraic, and you're taking integrals as many times. So the integral of e to the negative x is negative e to the negative x. The integral of that is positive e to the negative x. And because the formula is uv minus integral of v du, these plus and minus signs work out correctly. Connect your diagonals. So this is going to equal, we still have to use our limit notation, so be careful. This is the limit as b approaches infinity of the integral from 1 to b of, you could say u times dv if you want, or I'm just going to write out what I had. So I still have my limit notation. And then the antiderivative of this starts with me doing this kind of work. So I'll take care of negative exponents in a minute. So I've got negative e to the negative x times 1 minus x plus, because it's minus negative, e to the negative x. This would be integral of 0 times e to the negative x dx, so we don't need that term. And we're evaluating from 1 to b. When I plug b in, I'm going to rewrite so that I get rid of these negative exponents. So negative 1 minus x, or you could just say x minus 1, over, oh, sorry, not x though. Let's plug in b. So negative 1 minus b, or that's just b minus 1, over e to the x, which will be e to the b, plus 1 over e to the b. So that's plugging b in, minus, plug 1 in. So again, it's 1 minus 1, well, that's 0, over e to the first. And we're going to get plus 1 over e to the first. Okay, so now I can take limits. Now, technically, I could do a round of L'Hopital's on this, but this one, if it's algebraic over exponential, if it's easy to evaluate, thinking about function races, the denominator will grow much more quickly than the numerator. So we did this back in chapter 1. We can say that that's 0. 1 over infinity is 0, minus 0 over e, and then minus 1 over e. So we do get an answer. We get negative 1 over e. So this integral converges to negative 1 over e. All right, what about the next one? Now this has a place where I need to get rid of both the negative infinity and the positive infinity. And where you break this apart could vary, but I usually just pick 0. And then if 0 is not actually convenient when I go to evaluate, I can just change it to 1 or whatever makes sense, and I can go back and adjust my work that way. So we're going to split this up from negative infinity to 0, and then it'll pick up from 0 to infinity. So that means that I need the limit as a approaches negative infinity of the integral from a to 0 of this thing, e to the x over 1 plus e to the 2x dx, plus the limit as b approaches positive infinity of the integral from 0 to b of e to the x over 1 plus e to the 2x dx. All right, and now we have to figure out how to find this antiderivative. So this one looks kind of weird. U sub is not going to work. If u is 2x, that's not going to help me with my e to the x, or if u is e to the 2x, that's not going to help me there. So this is a hidden arctangent. A is 1. U squared is e to the 2x, because remember, that's e to the x squared. That's what e to the 2x is. So u is e to the x. So du is e to the x dx. So here's du over a squared plus u squared. All right, so once we get that established, limit as a approaches negative infinity of, so we said this was arctan, it's 1 over a, which is just 1. Arctangent of u over a, e to the x over 1 is just e to the x. Evaluate that from a to 0, and then we also are going to have the limit as b approaches infinity of the exact same antiderivative, because it's the same integral, just different bounds. And we're going from 0 to b. All right, now keep my limit notation and plug in the numbers. Arctangent of e to the 0, so arctangent of 1, minus arctangent of, be careful right here, it's e to the a, but pay attention what a is equal to. So I'm going to write e to the a, but I might make a note to myself, that's really 1 over e to the infinity, because it's e to the negative infinity. So Really, this is arctangent of, we haven't done the limit yet, but this will be arctangent of 0. Plus the limit as b approaches infinity of arctangent of e to the b. Now b is positive infinity, so that's not going to be an issue. That'll be arctangent of infinity minus arctangent of 0. Now we can take our limits. So the arctangent of 1 is pi over 4. The arctangent of 1 over e to the infinity, because a was negative infinity, is the arctangent of 0. So that's minus 0. Plus the arctangent of infinity is pi over 2 minus the arctangent of 0. Not 0, sorry, e to the 0. So minus the arctangent of 1, so minus pi over 4. So the pi over 4's cancel, and this is pi over 2. So this integral equals pi over 2, converges to pi over 2. All right, our last thing to talk about today are these, look at these short little integrals here, and then there's a theorem below it. So we're going to do these first two using the same way we've been using, and then we'll look at this theorem and apply it to these last 5 examples. So take a look at this. We're going to get rid of that infinity. So this is the limit as b approaches infinity of the integral from 1 to b. And I like to rewrite this. It's x to the negative 1/2 dx, just so I don't mess up something silly like a power rule. That's the limit as b approaches infinity of, so I add 1 to this exponent, I get x to the 1/2. And instead of dividing by 1/2, I'm going to say times 2 from 1 to b. And then fundamental theorem of calculus says plug that in. 2 square root b minus 2 square root 1. Finally, take the limit. 2 square root of infinity is infinity minus 2, which is still infinity. So this integral came out to infinity. It's not really equal to infinity. We probably shouldn't say that, but we can say that the integral diverges. It never stops adding up its area. Let's repeat that process. So this one, same idea, just different power. The limit as b approaches infinity of the integral from 1 to b of x to the negative third dx. So that's equal to the limit as b approaches infinity of x to the negative 2 divided by negative 2. I'm just going to write it like that. Fundamental theorem means plug in your b and your 1. So negative 1 over 2b squared minus negative, so plus 1 over 2 times 1 squared. Now in this case, negative 1 over infinity is 0 plus 1/2. So this integral does converge, and it converges to 1/2. All right, now we can always do these. They're quick little integrals. We can always do these the long way, or there is a theorem that you're allowed to use on your AP test. So these are called integrals in this form, the integral from any constant to infinity of 1 over x to the p. These are called p integrals. And you're allowed to use that terminology, like I said, on the AP test. So here's the rule. If the power down here in its positive form is greater than 1, then you're going to get that the integral converges. And furthermore, you have a formula for what it converges to. It converges to 1 over p minus 1. We can check the math on that. Here p was 3. 1 over 3 minus 1 is 1/2. So you're allowed to use this rule on the AP exam. It'll save you a lot of time. And we use it later in chapter 9 too. If this power is 1 or less, so 1 or a fraction less than 1, then the integral is going to diverge. So here p was 1/2 in the denominator, not negative 1/2, but what is it in the denominator? So it's 1/2. Therefore, we got divergence. So take a look at the next example. This is a p integral. So I would say this is a p integral where p is equal to 5/4. 5/4 is greater than 1. Therefore, the integral from 1 to infinity of dx over x to the 5/4 equals 1 over p minus 1. Well, that's 1 over 1/4. 1 over 1/4 is 4. If we did this the long way with limits and all of that, we should still get 4. So we get that this integral is equal to 4. It converges. And this is a p integral with p equal to 3/4, which is less than or equal to 1. So therefore, the integral from 1 to infinity of dx over x to the 3/4 diverges. All right, same thing with these last three. So let's just do a quick, if it converges, I'm not gonna write all this stuff out. So let's just do a quick thing. This is 2. So this p integral should converge to 1 over 2 minus 1. This is not a p integral. It's not a p integral because it's not 1 over x squared. If you were to write it in that form, it would be 1 to infinity of 1 over x to the negative 2, x to the negative 2. And the rules for p, we're really only looking for p to be above 0. But I guess I could still use this rule. P is technically less than or equal to 1, but I know that this integral diverges without doing any math because x squared is, let's say y equals, x squared is an increasing function. And if we're saying what's the area of this increasing function from 1 to infinity, that area is just going to continue to grow larger and larger, right? Last one, e. E is greater than 1, so therefore this converges to 1 over e minus 1. All right, that's it for today. Come to office hours if you need help with any of this.